In this video, we'll learn about the process of X-ray generation and its atomic basis of X-ray production in an X-ray tube. So before watching this video, please go to our channel and watch X-ray tube video where I've explained the structure of X-ray tube part 1 and part 2. Then we'll learn how X-rays are getting generated in an X-ray tube. My name is Dr. Aishwarya. Going to very much basics, we see the structure of an atom where atom contains nucleus containing protons and neutrons within. Then it contains various elliptical or circular orbits in which orbital electrons are present. Each orbit has been given a standard labeling, that is K, L, M and so on. They are also called as K shell, L shell and M shell and so on. When electron from the lower energy shell gains energy, it jumps to the higher energy level by receiving the energy. The opposite happens when higher energy level electron jumps to a lower energy level. It releases energy in the form of electromagnetic radiation. When excess of energy is given to the inner shell electrons, the amount of energy may be such that the electron can get emitted out or ejected out of the atom. What happens in an X-ray tube is, when the cathode filament made of tungsten is heated up to a certain limit, it emits electrons which bombard the anode or the target material, where kinetic energy of the bombarding electrons is converted into heat, where 99% converted into heat and 1% is converted into X-rays. Now we'll see in detail what happens at the anode level. Anode is made of tungsten. When electrons with the kinetic energy bombard the anode, they lose their kinetic energy in three ways. One is excitation, ionization and radiation. Any of these three methods can occur at the level of anode. We'll see individually what does excitation, ionization and radiation mean. So if this is the atom and kinetic energy is used for the electron to jump to higher level or the higher orbital level, it's called as excitation. In ionization, the kinetic energy is used to eject the orbital electron out of the atom. By losing this electron, the atom is now positively charged or ionized. In radiation, the kinetic energy of electron is just used for the change in direction, where energy is released in the form of a charged particle or a wave that happens due to change in direction. So this is excitation, ionization and radiation. X-ray is produced at the level of anode using two mechanisms. One is called Bremsstrahlung radiation, which uses the principle of radiation. Next is the characteristic radiation, which uses the principle of either excitation or ionization. Bremsstrahlung contributes to majority of the X-ray production. We'll see them in detail. First is the Bremsstrahlung radiation, in which electron passing near to the nucleus is decelerated and deflected, and that excessive energy is released in the form of braking radiation or Bremsstrahlung X-ray. If electron goes close to the nucleus, it is deflected even more, angle of deflection varies and different energy braking radiation is released. So the amount of deceleration varies, hence the energy released also varies. So the X-ray from Bremsstrahlung radiation contains photons of different energy levels, or they are heterogeneous beam of X-rays. Maximum energy X-ray photon is released when electron directly bombards the nucleus, where all of its kinetic energy is converted into an X-ray photon and the bombarded electron diminishes. If electron passes very close to the nucleus, it is deflected and retains very little of the kinetic energy. Majority is converted into X-rays, so that X-ray photon will have some moderate to high energy. Next, we'll see when electron passes away or little far from the nucleus, it retains majority of its primary kinetic energy and very little of its kinetic energy is converted into photon. So these X-rays will have the lowest energy. if electron directly bombards with orbital electron without influence of nucleus, then it will result in heat production, not X-ray production. So the energy of the X-ray beam, which is released due to Bremsstrahlung mechanism, depends on various factors. We already discussed, now we'll list it out. It depends on the energy of the primary incident electron or its kinetic energy. Next, it is determined by how close the electron passes to the nucleus. Yes, and next, the third factor is it also depends on the atomic number of the atom on which the electron is incident, determines the strength of the nuclear pull. X-ray from the Bremsstrahlung radiation is heterogeneous, contains X-ray photons of different energies. So we'll graph it out where y-axis shows relative output, x-axis shows energy in kiloelectron volt of X-ray photons. So the graph is somewhat like this, where photon energies are distributed in almost all energy levels. It's called as continuous spectrum. Hence, Bremsstrahlung radiation is also called as general radiation, or because of its mechanism, it's also called as braking radiation. These are the other names of Bremsstrahlung radiation. Coming to the next most important mechanism, characteristic radiation, in which electron reacts with the K-shell electron or the innermost shell orbital electron and ejects it out of the atom. Now the ejected atom is called as a free electron, and the resultant daughter atom will be ionized because an empty space is created, which is called as hole, which is later filled by the higher energy electron jumping to this lower energy level. Now we can see the higher energy electron jumps to the lower energy level. What happens? We already learned. It releases the excess energy in the form of electromagnetic radiation, which is nothing but X-ray production. This is an X-ray, which is also called as characteristic radiation. We'll apply this mechanism to the tungsten atom, which is present in the anode. Now the electron comes with a specific kinetic energy, interacts with the K shell or innermost shell electron and releases it out of the atom. K shell in tungsten has 70 kiloelectron volt, L shell has 11 kiloelectron volt energy level. So the energy of the bombarded electron should be more than 70 kiloelectron volt in order to release the orbital electron out of the atom. Then the higher energy level electron jumps to lower energy level by releasing X-ray, which has an energy which is a difference of energy level between K and L shell. So what is the difference between K and L shell? 70 minus 11, that is 59 kilo electron volt. So the X-ray photon which is released when electron jumps down will have an energy of 59 kilo electron volt, and this 59 is characteristic number for tungsten atom. So different atoms will have different X-ray energy levels which are released, hence it is characteristic for a different specific atom. That's why the name characteristic radiation is given. So for molybdenum, which is used as a target in mammography X-rays, the characteristic radiation or the X-ray photon will have energy level somewhere around 17.5 to 19. We'll draw the graphical representation of characteristic radiation. Same graph where y-axis is output, x-axis is the energy in kiloelectron volt. That was the Bremsstrahlung curve which we drew. Now the characteristic radiation for tungsten somewhere around 59, molybdenum falls around 17 kilo electron volt, and this is the graph for characteristic radiation, and the area under the curve represents the quantity of X-ray. We look at two important concepts, that is quantity and quality of X-ray. Quantity in simpler terms is the number of X-ray photons in an X-ray beam. That is represented by area under the curve. It sums the intensity of the X-ray. Quality is the energy distribution or the shape of curve. higher the quality, higher energy X-ray photons are present in the beam. So better image quality, lower exposure or radiation dose to the patient. In general X-ray tube, characteristic radiation is 20%, Bremsstrahlung is more majority or 80%. So what are the factors affecting the X-ray spectrum? First one is the potential difference or the KVP which is applied between cathode and anode. As we define X-ray in the form of quantity and quality, quantity or area under the curve is directly proportional to square of the KVP and quality is directly proportional to the KVP. So there is maximum photon energy beam and presence or absence of characteristic radiation depends on the KVP applied. So now how does the graph change? At a fixed filament current, we go on increasing the KVP. The area under the curve goes on increasing, that is the quantity of X-rays increases. Also the high energy photons will also increase. So at high KVP, more energy X-ray beam is produced. So the quality of X-ray beam also increases. Next factor which affects the X-ray spectrum is the tube current or the MA, milliamperes. So quantity of X-ray directly depends on MA into exposure time, that is MAS, but it has no effect on the quality of the X-ray beam. So as you increase the current, quantity increases, quality does not change. We'll graph it out. At fixed KVP, we go on increasing the MA. So area under the curve increases, that is quantity of X-ray increases, but the area in which the high energy beam falls is the same. That is quality of X-ray does not change by increasing the MA. Third factor affecting the spectrum is the atomic number of the target. Both quantity and quality are directly proportional to atomic number. That means atomic number increases, quality, quantity both increases, also determines the characteristic radiation. Fourth factor is filtration. When filter is applied to the resultant X-ray beam, it absorbs low energy photons. So number of photons decreases, that is quantity decreases. But the overall energy of resultant X-ray beam increases because low energy photons are absorbed, high energy are passing through. So quality of the resultant beam increases. When we draw it, now this is the high energy in red, low energy in light red. Filter is applied, low energy beam is absorbed. So out of 6 photons, only 4 come out, that is quantity decreases, but high energy beam comes out, so quality increases. Next and the last factor affecting the X-ray spectrum is the voltage ripple. When voltage is applied across cathode and anode, it shows a ripple. Ripple is nothing but small unwanted residual periodic variation in the DC output when it is converted from AC output. The single phase generators have 100% voltage ripple, but the newer triple phase generators has only 5% voltage ripple. So the quantity and quality are better in a triple phase generator. So lesser the voltage ripple, higher the quality, higher the quantity. That's all about the process of X-ray generation. For more physics videos, please comment down below what you need and follow our page Radiology Doodles. Thank you.